Chapter 10, Verification and Validation, Part 2. In the previous part, we saw that the simulation model is not behaving like the real system. So we let's say we do further investigation, and by doing that we find that, oh, the model contains two unstated assumptions. So the first one is, when a car arrives to find the window available, the teller begins servicing immediately. So this is one of our assumptions in the simulation model, and we have another assumption here: there is no delay between one service ending and next beginning. So we need to go to the real system to see if these two assumptions are correct. So after further investigation, we find that, oh, the first assumption is not valid. It's not correct because the teller has other duties. So when there is no car present, the teller may be busy for serving a walk-in customer. So when a car arrives, maybe that service cannot be started right away. So in order to modify the simulation model, we need to consider servicing the walk-in customers as well in our simulation model. And again, here we obtain that the service for walk-in customers is based on exponential distribution with 3 mins. So yeah, let's say we have modified our simulation model for the first assumption. The second assumption, we see that, oh, it's approximately correct, so we don't need to do further adjustment in our simulation model. So let's see how the modified simulation model works now. So we run the modified simulation model for, again, with the same number of replications, and here we do have the results. Now we calculate the y bar, I mean the average of the sample data, which now becomes 4.78 minutes, and the standard deviation, again, for the sample data, it becomes 1.66 minutes. Okay, so again, we apply that hypothesis test here, and by having the new number, the new values for y bar and s, t0 becomes now 0.710, and now you see that that number lies exactly between the interval of minus 2.57 and 2.57. So now we fail to reject the null hypothesis, right? So yeah, so this is how we do for any simulation model. So we run the test, hypothesis test. So by this statistical method, hypothesis test, by using t distribution, we can compare the simulation model's result with the real system, and if we see that it's not validated, so we need to figure out what's the problem, and then we need to fix the simulation model, and after that, again, we run the simulation model, obtain the sample data, and run the hypothesis test until we actually obtain a modified version of the simulation model, which will be validated. Okay, let's have a review here for statistics. For any hypothesis test, we do have two types of errors. Type 1 error is rejecting H0 when H0 is true. Okay, so when we have a significance level alpha like 5%, that means that the probability of having type 1 error is alpha. So when we have it as 5%, this means that with 5% probability, we may reject the true hypothesis. So that's the probability of having type 1 error. Okay, and the second error, type 2 error here, is accepting H0 when H0 is false. Okay, so and we showed this by beta. So the beta is the probability of failing to reject H0 when H0 is actually false. Okay, so and among these two errors, we see that the type 2 error, the type 2 has more severe consequences than type 1. Because if you reject the true hypothesis by 5% chance, so you have rejected that simulation model, right? We're not going to use that simulation model in order to infer and have insight to make changes in your real system, and that's it, right? But when you accept a false hypothesis, I mean that simulation model is not a true representative of the real system, and you accept that, you accept that, and then you go for changes in the real system based on a false simulation model, and that has more severe consequences, right? So because of that, here we do have one measure which is called power of test, and it is 1 minus beta. Okay, the power of a hypothesis test depends on two factors: sample size n, and the true difference between sample mean and population mean. So here the population mean is the mean obtained by the real system, and the sample mean is obtained by the data from the simulation model. So the delta as the true difference is this. So the absolute difference between the sample mean and population mean divided by the sigma, and the sigma here is the population standard deviation. Okay, and we can estimate that standard deviation by sigma hat as S obtained by the sample data. Okay, so that's the true difference. So by having this equation, we can obtain, and assuming a target on the absolute difference between the real system and the simulation model, and also having a target on the value of the power of test, we can obtain the sample size. I mean, what should be the sample size in order to have a minimum level for power of the test. Okay, so here, for example, for our example, if we assume that 1 minute as the absolute difference between the sample mean and the population mean is reasonable for us. Okay, so for by having this and having the S as the sigma hat from the sample data, we can obtain the delta hat as 0.6. Okay, so estimation for the true difference, delta hat as 0.6, and let's say that the power of test as 90% is okay for us. So the beta, I mean the type 2 error, can be at most 10%. Okay, so now in order to obtain the sample size, we have OC curves here obtained by the two-sided t-test, OC curves, operating characteristics curves. Okay, and in the horizontal axis, we have the standardized difference D, which is the delta hat. Okay, I mean estimation for the true difference. And in the vertical, we do have the probability of not detecting a difference, or beta. Okay, I mean the type 2 error. So here, since we want to have 90% as power of test, 1 minus beta as 90%, then the beta should be less than or equal to 10%, right? 0.10. So as you see here, the delta hat, the estimation for the true difference is 0.6, which falls here, right? And if we go up in order to find a curve with with let's say 10% as 0.1 for the beta. Here we cross the curve for 30, right? As you see here, we cross the curve of 30, so that means that the sample size should be 30. So for our example, if we want to have our hypothesis test with a power of 90%, then we need more sample data. Now we do have 6, but it's not enough. We need to have 30 replications. Then by having that 30 replications, we can say the power of our test is 90%. Okay.